So this is Lab 2 for Physics 2211, and I am Jane Witecki. In this lab, we'll be analyzing the motion of a falling object that is dropped from rest and falls down to the floor. For the falling object, I analyzed a crumpled up piece of paper and used Tracker to analyze its movement over time. For a falling object, the forces acting on it are the force of gravity going down and force of drag pulling up on it. The force of drag and gravity do not cancel, which causes the object to accelerate over time, and if given enough height, it will reach its terminal velocity. Here are some formulas I used for this lab. I used the velocity update formula, and I used the position update formula. I also have the force due to gravity, which is F equals negative mg, where g equals 9.8 meters per second squared, which is the force of gravity. It's going to be negative 9.8 as it is being pulled down to the earth. Here is a diagram showing the forces again. Drag pulls up and gravity pushes down. I analyzed the paper ball in Tracker, taking point mass points along the coordinate axis that the paper falls on over time. This created a position versus time graph on the right on the top, as well as a chart of values we can use to compare to our computational models in the future. So here is our computational model for just the gravity. This does not account for the drag. We can see this as p equals 0, and we are not calculating drag force and just calculating net force for our loop. The loop goes to 0.433 seconds, as this was the experiment time, and the mass of the ball, the crumpled up piece of paper, I calculated to be 0.1 kilograms, and I used a delta t of 1 over 30 because that was the frame rate that was used in the video. Here's our computational model for gravity. With the addition of drag force, we needed to update the value of b, which I found through trial and error, and use it to calculate the force of the drag, which is added on to the net force calculation, which then leads to velocity update and position updates, causing an effective drag on the results compared to when you're not calculating a drag, as was previously. You can see that in the formulas. So here is the graph. Analyzing our graph with the observed versus computational model results, we see that in our computational model, including drag, the result eventually lines back up with the experiment, showing that it is being affected by drag in the computation, whereas the computational model with just gravity continues in the same fashion over time without a significant drop, with the drag calculation as it is expected to fall at a faster rate than with the drag from the calculation. So some what ifs. Which models predicted terminal velocity? The model with the drag being accounted for predicts terminal velocity, as the drag force is just when it is equal and opposite to weight, which is found from when you're calculating the drag in that computational model. So if the object is thrown downward, we can see that all the terminal velocity is just the velocity needed for the drag to be equal and opposite to its weight. So this would happen regardless. Although the initial velocity would be faster, it would still reach terminal velocity in the same way as the computational model did. It would just have a faster initial velocity. That is it for the lab. Thank you for your time. Have a good day.